Kind of really to talk about things this way for a reason. US taxes.
Hello?
Which is neither of these things fit well with what Democratic Party messaging like anything.
Hi, can everyone online see the screen and the audio?
Yes.
Yes, okay. Let's make it a little louder. Okay. I think this is everyone that's going to show up to this session. So this afternoon, we are very pleased to have the Adjoint School presentations. And I'm going to tell you a little bit about what the Adjoint School is. But first, I want to make sure we acknowledge all of the organizers. That includes myself, Elena, and Nathan, and Anna. So Anna, you're probably online, right? Yeah, and so what you can see on the screen is that we have lovely artifacts from the past week. And what you'll be hearing today are 20-minute presentations about the work that they worked on over the course of the whole school, but also over the course of the research week. So I just want to also acknowledge all of the mentors and TAs, as well as students who have participated in the program. It's a very extensive program. It ran for 20 weeks, and the mentors and TAs and students were engaged through the whole program. So I think we should really applaud them for the effort that they put in, because this is a volunteer effort, and yeah, basically it. Okay, so let's give a round of applause. Okay, and for those who are unfamiliar with the Adjoint School, I just wanted to put up a little summary of what the school is about. Basically, it's an approximately 20-week research school where students learn to read, write, and present in the language of applied category theory, mentored by an expert in the field. And the school could be factored into 3 different portions. The first is a reading seminar, and this runs for about 16 weeks, where the students give a presentation about a paper that the mentor has selected. And then we also have a blog post that will be on the N Category Cafe shortly, maybe in the next couple weeks. And then the last thing is the 1-week-long research week that occurred in person at the Arib building at University of Maryland. Okay, so if anyone is interested in becoming a mentor or a TA, please feel free to reach out to Nathan or Anna. They will be taking over the next year. So if you have interest there, please feel free to reach out to them. And then if you're interested in becoming a student for the school, the applications typically open in December, and we accept undergraduates, PhD students, postdocs, as well as people working outside of academia. So if you're interested, just keep an eye out on the Adjoint School website. Okay, so with that, I think we can move on to the presentations, and they will occur in the order that they're presented on the website. So I believe the first presentation is Priya. Yes? Okay. All right, so can we have Priya's group come up here and join the Zoom and share their screen?
Hello, my name's Isaiah, and this is Brandon, and today we'll talk about applications of message passing. So our group was particularly interested in in a topic called linear logic, and one of the most fascinating areas in linear logic is this mathematical construct called the linear actagory. And what makes linear actagories a very nice mathematical construction is it gives us a nice and formal framework to describe horizontal, if you will, um, horizontal communication of information. So last week during research week, we set out to study the application of message passing to some protocols, and but instead of using the full framework of linear actagories, we used a framework developed by Chad Nestor called the free cornering, which is intimately related to linear actagories, as the horizontal component of free cornering is linear actagory. So in this short presentation, we will cover three topics. We'll discuss what a free cornering is. We'll give a real-world application. And if we have time, we might discuss free cornering with choice when the base category that we're working with is compact closed. So to get started, we need to think, what exactly is the information we want to communicate? And what we are actually communicating are resources, and the structure we'll be using is called the resource theory, and that's really just a very fancy name to a very simple categorical structure. It's actually just a freely generated strict symmetric monoidal category, where the objects are resources like egg, pepper, or stove, and the morphisms are processes that transform resources. So for example, we might have a morphism like crack, which denotes the process where we crack an egg and turn it to yolk. Or you may have a process like fry, where we take the yolk and a stove and get sunny side up in a stove. And we interpret tensor to be and. So we would say egg tensor pepper represents having both egg and pepper. So before we can actually define what a free cornering is, we'll need two mathematical constructs. We'll need a double category, in particular a single object double category, which will consist of three key pieces of information: two monoids, which we call a horizontal edge monoid and a vertical edge monoid, which are, if you can see, here and here. And a collection of cells. So if you know monoidal graphical calculus, you can think of reading these cells top to bottom, and this is sort of your regular diagram, except we have these two side lines, and that will represent our communication of information from one cell to another. So the objects on the top and bottom cell come from a horizontal monoid, and the objects on the side cells come from our vertical monoid. And of course, we can compose these cells horizontally and vertically. The second structure we'll need is a pro-arrow equipment. So a single object double category is a pro-arrow equipment when for every object in our horizontal monoid, we have this A white circle and A black circle in our vertical monoid, and we have these four cells. So the interpretation for this free cornering, as we'll soon see, is that A white circle will represent sending a resource from left to right, and A black circle will represent sending a resource from right to left. So for example, this corner cell here, if you can see my mouse, yeah, will represent taking a resource A and sending it from left to right. And these corners need to satisfy a handful of what we call yanking equations, and they actually have a very natural interpretation. So for example, this one on the far left is just saying that if we receive info A from the right, and then we send A from left to right, then it's like doing nothing, which is sort of what we would expect. So with that intuition, we're now actually going to describe this monoid, which will encode the data we need of sending information. In particular, we'll have this A-valued exchanges, which is just a free monoid created from the set where we have, we're created by taking every object A and having an A white circle and A black circle. So the intuition is that elements of the A-valued exchanges describe a sequence of resources moving between participants in an exchange. So here's just an illustration of one object in this monoid A-valued exchanges. We have A black circle, B white circle, and C white circle tensored together. And what that really denotes is if we have Alice on the left and Bob on the right, it denotes Bob sending A to Alice because it's a black circle, and because the other two are white circles, those represent Alice sending B to Bob and then C to Bob. So that's what an A-valued exchange is. So now we have the necessary structures to create a free cornering. And so to do that, we start with a resource theory, which, as you remember, is just a strict symmetric monoidal category. And we define pro-air equipment A, where we have a horizontal monoid, which just inherits the monoidal structure from the base category A. We have a vertical monoid, which are just the A-valued exchanges. And then we have these generating morphisms, which are the white corners and the black corners, along with the vertical cells for each morphism in the base category. So if we have a morphism F A to B, we have this vertical cell, and they need to satisfy a bunch of rules to behave nicely. For example, the vertical composition of vertical cells needs to be the vertical cell of just the composition of the morphisms in the base category, and we have similar results for identity and tensor, similar equations. So how does a free cornering capture concurrency or message passing? The interpretation you should have is that the horizontal monoid of the free cornering represents the resources, and the vertical monoid of the free cornering represents the channels where we're sending information. And the cells are what Chad Nestor called concurrent transformations. And what these cells do is they describe a way to transform the top elements, the top resources to the bottom resources via information being passed from the sides. So here's an example where we crack an egg and we then send the yolk to the area of the stove where we fry it. But there's one ingredient missing in this framework, which is the ability to dynamically choose which resource we want to send. Unfortunately for our group, Chad Nestor solved that a few months ago with a paper describing free cornering with choice, and he also did with iteration, but for now we're just going to focus on choice. So basically, when we have we start with a symmetric distributive category, and in this case we need a distributive category because we'll have a notion of or, so we can have egg or pepper, which we denote with O plus instead of O times. And we have just a regular free cornering, and we add to our regular free cornering a few additional properties. First of all, for all pairs of A-valued exchanges UV, we add these U plus V and U times V objects, and these will be the types we'll use for a choice. And then we have three properties that give us our choice. So we start with first choice on the left, which is mathematically given by this diagram. So basically for all cells alpha and beta that only differ by the left boundary, so you have X here and Z here, there exists these injection-like cells, which are represented by these upside down pies and a unique cell, alpha plus beta, such that when we apply these injection-like cells to this unique cell, this unique composite cell, we actually recover alpha and beta. So we basically have this choice, this ability to choose which morphism we want. And then we just have a few more of these properties, but they're just for the different sides. This represents on the right. So we have two cells just different by the right. And instead of having upside down pies, we have pies that act more like projection maps and go on the other side. And similarly, we have choice on the top, where we use these injection maps on the top, denoted by sigma, to recover alpha or beta. So that is the general framework we used in our research. So now we're going to actually see what we did to apply this framework to a real-world problem, and I'll hand over the microphone to Brandon to explain that.
Thanks, Isaiah. So, yesterday you saw I'm an engineer, so I'm trying to study processes in complex systems, and we've been using, the symmetric monodal category formalism to try and represent processes. But what that doesn't allow me to do, as Isaiah was pointing out, is sort of decompose the different subsystems and figure out how they're all working concurrently as one process. And so that's where we really wanted to apply this framework to an actual problem that I've been working on as an engineer. And so this has real sort of meaning and implications for safety and health of people working in, manufacturing facilities or plants where there's operations that are hazardous and we need to have safe protocols. So the situation, we call it isolation of hazardous energy in industry. And what this means is occasionally a human has to go into a tank or a confined space, as we call it, to clean a tank or perform a service on equipment. And sometimes that equipment has other sort of things going on, like rotating devices that are, connected to power sources. And so we have a very manual protocol today where humans have to sort of make sure and guarantee that the system is safe in terms of power is off when a human enters, right? Because we don't want them to get sort of caught up in the rotating equipment, for instance. And so I've seen this happen before, like the accidents can happen. And so what we're looking for is a more formal way to describe this exchange of information in these sort of concurrent choices that are being made. And can we represent in a way that can sort of guarantee that only when the system has reached a safe state does the human enter to perform the work. And so I've been sort of using other formal methods like model checkers and sort of Petri nets to try and find the right abstraction for this. And we thought it was a good chance to try out a ACT framework. So this is sort of the conceptual sketch of what's going on here in this example. Imagine you've got two pieces of equipment, a tank and a power source that's sort of feeding power into the tank. Now imagine that the tank is sort of able to check and inform a worker who's over that piece of equipment whether or not it's clean or needs service, right? So we see that sort of information being passed that signifying to Alice that the tank needs cleaned. And so what Alice needs to do is sort of generate we call it a work order, like somehow communicate with Bob to say, because Bob's controlling another piece of the facility, which is the power source, and say, hey, can we turn the power off, shut it down, so that I can then safely enter the tank. And so we want a formal way to describe this process and its sort of concurrency so that we don't run into a situation where someone enters the tank when it's in the system is in an unsafe state. And so, we'll put this framework to use. So we define our category, isolation of hazardous energy, as the free, strict, symmetric monoidal category. And as objects in this category, we're considering the states that I was sort of describing. So whether the tank is empty or not, whether the power is on or off, whether the tank is dirty or not. So those are our objects in this category. And for morphisms, we're looking at processes that transform those states. So for instance, if I had the power was on and we shut it down, it's now off. And so we sort of can lay out those different morphisms. And this is sort of our finished product for the research week in a way. It's describing that full process. But now we have the ability to sort of show the subsystems that are each doing their individual thing, like the tank, Alice, and Bob, right? So now we can able to represent those and then show, not only reading it top to bottom how the work is being done and as states are changing, but also left to right with the cornering concept that Isaiah was describing to show how information is being passed along. And so, just sort of to walk through this very quickly because we're sort of short on time. If you start with a tank, you can sort of check to see if it's clean or not. From there, if it is in the state of it needs service, then it creates a work order, which is then copied. Copy is sent to both Alice and Bob. That lets Bob know to shut down the power. And once all those conditions are met and the safe enter cell, then Alice can enter the tank, perform the work, and then everything sort of updates and propagates through. And so that's sort of our industry example, and I'll turn it back to Isaiah to take it home.
Yeah, so basically how the circuit is working is it's just a very complicated conditional. So each of these cells can be broken up into simpler cells. So if you look at safe enter, this is representing when it's safe for Alice to enter the tank. And there, you can see that there are a few conditionals. So remember, plus was the type representing a conditional. So here we have, for example, around safe enter, we have a choice between having a work order and we're using monoidal unit for not having a work order. And on the right, we have the choice of the system being on or off. And then we sort of propagate those choices down. So in the next slide, I'm going to show exactly how we guarantee that we enter safely. So here's how the safe enter is defined. Remember the uniqueness property from the free cornering? Well, what we're going to do is we're actually going to define the safe enter cell for every single possible choice. So in this case, what we're going to define safe enter when we choose work orders or when we have a work order, when the tank is empty, and when the power is off, we know it's safe to enter and we should enter. Otherwise, we basically do nothing. We just propagate the choices down. Now, one of the things to note about the way we're formulating things is we start with these input choices, and when we evaluate, the choices sort of propagate through the cells. And actually, that is how we think we can create a formal way to verify whether a system is safe. So for example, we can say that if we start with one of these check mark states as an input, and all of those represent safe starting states. Remember that sigma 1 and pi naught here represent the power being on and the tank being occupied, which is something we don't want. That's why there's X's next to them. So if we start with one of the checkmark states, you can show that this cell will remain in a checkmark state. And if you compose it with another cell that is safe in this sense, then you're going to get another safe cell. You're going to get a safe composite. So you have this composable safety, which we think is interesting. So how much more time we have?
I think this is probably good.
Okay, so I think I'll just briefly mention the next topic. So that was how we were applying this free cornering to these real world problems, but we also wanted to apply it to a little less real world problems. So what we want to do, another thing we want to model is quantum protocols and use this free cornering framework to express those. And the natural choice would be to have as the base category the category finite dimensional Hilbert space, or FD-Hilb. Now we haven't worked out the details assuming the base category is FD-Hilb, but we started with just showing what happens when the base category is compact closed. So I'll just briefly mention, I won't go over all the proofs, but one of the things that Chad Nestor showed, I think back in 2022, is that if the base category is compact closed, then if you just take the horizontal component of the free cornering, and what that means is just the collection of cells that are purely horizontal, then you get a symmetric monoidal category, and you get a category that is compact closed, more importantly. But what we wanted to do is we wanted to expand the result a little bit. We wanted to show that this we have a similar theorem if we are using the free cornering with choice added. So we have some math, which I'll skip, and we basically have this interesting result that if the base category is compact closed, then the horizontal component of the free cornering with choice added is also compact closed. And as the final result, which I think is personally one of the coolest results we found, since the category is compact closed, we can talk about transposes. And you get this interesting relationship between choice on the left and choice on the right. In particular, what you get is that this upside down pi naught function, if you consider the upside down pi naught function, which is our choice on the left, and we take the transpose of it, we actually get the pi map correct in the correct orientation. And so you have that interesting relationship. So that's our talk. Those are the results we found. And here are the references we used.
Thank you, Brandon and Isaiah. So we have room for one quick question. All right.
Hey, yeah, this is great. I've got to put on my engineering hat for a second. And so I kind of have a question. It's kind of a two-part. One is, can you start reading that diagram from the middle?
Yeah, let me just, sorry, I accidentally closed the Zoom.
Question. All right.
Hey, yeah, this is great. I've got to put on my engineering hat for a second. And so I kind of have a question. It's kind of a two-part. One is, can you start reading that diagram from the middle?
Yeah, let me just, sorry, I accidentally closed the Zoom. Okay, so the big diagram, the messy one?
From the right.
one?
And the reason why I say that is because I'm thinking about fault tolerance, and I'm thinking about the case where maybe there's some sort of power jitter, and now maybe some of the states that you've been propagating through, and you're in the middle of some chain of computations where you're trying to figure out if it's safe to enter. So, yeah, I'm thinking about fault tolerance of this system in practice.
No, I think there's a lot of work to be done to sort of apply it in an actual application. We just wanted to see if even this framework could even represent this sort of protocol. Like you could represent this in a number of different ways, as you would like software model checkers or something. But yeah, I mean, that's definitely something to consider.
Great. All right. Thank you. Thank you. And this group was mentored by Priya. Do we have anyone from Barbara's group in person, or are they all on Zoom? Okay. All right. So Johanna.
Hello. Can you all hear me well?
Yes, we can hear you.
Okay, great. Let me just,
There we go.
and I should probably get it into. Are the slides looking?
Can you actually make them full screen?
Yeah, I'm trying to. Let me just, it's been a while.
Oh, sure.
Sorry, let me just pause it and try and open it again for a second. Okay.
Great. Thank you.
All right, lovely. Okay, so So we talked that I will begin the presentation and then Paul will take over. Does that sound good to the people in the room? Is it good enough to hear?
Yes.
Yes. Okay, great. Okay, so hi, hello. So I will first talk a little bit about the work that the behavioral metrics group did. So we were led by Barbara and TA'd by Sebastian and Paul, and there were 5 students in our group. So there was Avi, Carrie, me, Martina, and Wojtek. And we will especially go into the idea of compositionality of a particular lifting called the Kantorovich lifting, and mention also an application in up-to techniques, which we focused a little bit on in the research week and are definitely eager to go forward with in the future as well. So that's a future research direction as well. Yeah, so at first, yes, so, oh, the slides, yeah, okay, they changed now. So the table of contents, so at first we will just introduce the topic of behavioral metrics briefly, and mention a few different kinds of coalgebras which are relevant in this discussion. And then we will really dive into more the mathematical gears that you need to get, like quantiles and what categories we're working in. And then I will define the Kantorovich lifting, and then after that, Paul will dive into what compositionality exactly means, what results we have, and also how we can use it to lift natural transformations and why that might be important. Yeah. So for the introduction, so the reason we care about lifting functors into, so usually we have functors on set, and then we want to lift them into some category that has a forgetful functor into set. But the motivation for that is that there is this idea of coalgebras for endofunctors. And they are used in different ways to model transition systems of various kinds. So for example, to model deterministic finite automata, Kripke frames, label transition systems, probabilistic transition systems. And what they have in common is that they can all be modeled as these functions from a set X into the image of that set X under a specific functor. So for deterministic finite automata, that functor, for example, would take X to the product of the 2-element set and all the functions from and given alphabet A into X. And now something that is also well studied in the field of coalgebra is behavioral equivalence. And that means that in broad strokes, the automata or transition systems, they behave the same way. And that can be modeled using final coalgebra, which we're not really getting into, but it kind of yields these different notions of equivalence for different transition systems. And it's robust and it works, but it's maybe a little bit rigid at times. But yeah, so the coalgebra definition is that if we have an endofunctor f from C to C, then a coalgebra is just an arrow in that category from X to Fx. And now equivalence is definitely very useful, but sometimes, especially with maybe in certain more quantitative settings, it might be more useful to consider behavioral distance. So here we have this this automaton in the probabilistic setting. So we have a probabilistic transition system. And if you look at the states X and Y, then X, so Y, let's start with Y, actually, that's a simpler one. So Y has the probability, half probability to go into U and half probability to go into V. And whereas X has almost, for some sort of given epsilon, almost the same probability to go into U and V, especially if epsilon is small. Well, if epsilon is large, then that doesn't really hold. But given that it's very small, then we might want to express that these two states are actually similar, even though they're not the same. And if epsilon gets really small, then it might be, we might want to have some ways of quantifying that. So that is really the motivation of the behavioral distance. And looking at the other two states which we haven't mentioned, so U and V. For example, we can see that V doesn't have any arrows going out of it. So V is a trap state, and it's modeled by the one in the signature of the transition system. And so we may want to say that a trap state and a non-trap state are completely different. So they're maximally different. So here they would have the distance 1, if we say 1 is the maximum distance. So there are various things to express about these systems with distance. And now, if we have a lifting, which is given by this commutative diagram with forgetful functors, then we can also find the behavioral distance. Now first, a lifting means that if we have a functor on set, and we go into the category, well, here we have taken pseudometric spaces. So pseudometric spaces, the objects are pseudometric spaces, and the morphisms between them we have taken to be non-expansive maps. They work well for this work, but they're not the only choice. But here, if we lift a functor on set to pseudometric spaces, it means that for every pseudometric space x, d, we give a new pseudometric space fx with a new pseudometric, and that new pseudometric is really the way you define it gives an important part of the lifting. And we can use this new distance that we defined on fx to find the behavioral distance between two states. And how we do that is that we define behavioral distance as we define behavioral distance as the greatest fixed point of a function. And that function takes a pseudometric on x and gives a new pseudometric on x using the lifted metric on fx. So it precomposes that metric on fx with the coalgebra function. And doing so and finding the greatest fixed point of that function gives us actually the behavioral distance. And now, for example, if we want to look at a quick example here, then here we have this coalgebra, which is a deterministic automaton with now not a 2-element set as it's which indicates whether it is an accepting or a reject accepting or state or not, but we have a continuous unit interval that expresses a fuzzy measure of how accepting a state can be. And now the induced metric, if we start out with some sort of a metric on the space, then the induced metric gives us the maximum between the fuzzy expression of acceptingness and the distance of A successors and distance of B successors. And now, if we take the first metric to just be the 0 metric, which makes our job a little bit easier, then at first we get that the distance between x and y is 0.2, because we see that the only non-zero element in the maximum, the set over which we find the maximum is 0.5 minus 0.3. So at first we get 0.2 over there, then we get the distance between y and z to be 0.5, and between x and z to be 0.7. But now if we look at the distance between x and y, what we get is that that doesn't actually remain at 0.2, because on the second step, we take, again, we have the maximum over the difference, 0.5 minus 0.3, which is still 0.2. But now we take the previous distance that we obtained on the A successors and the B successors. And now we see that with the A successors, we get the distance d of y and z, which we got in the previous step, that it is 0.5. And similarly, if we take the B successors, then we get the distance of z and y, which is also 0.5. So in fact, we see that at depth 2, the distance between x and y changes. And so that's how and then if we find the fixed point of this process, then that gives us the behavioral distance between two states. So maybe that illustrated a little bit of how this process works. Yeah, so now I will go on to quantiles and what categories we're really looking at. And so for that, first we have a quantile V, which is, so first we should define a quantile. So that's a complete lattice with an associative operation, and it distributes on both sides over arbitrary joins. And now if this operation has a unit, then that unit is denoted by 1. And it turns out that we can actually use this associative operation to also define a distance function on the quantile, and that is very handy for us. Some examples of quantiles are, for example, the two-element set with the associative operation being and, I believe, and also the unit interval with truncated addition. And now we are going to look at quantile valued predicates and quantile valued relations. And that just gives us that, those just mean maps from X to V and maps from X cross X to V. And now these, we take quite a loose sense of relation, but actually we're going to make it more rigid in a second, and we're going to impose reflexivity and transitivity, which will make it look more like a metric. But first we just consider relations. And now building on these predicates and predicates and relations, we have the categories vpred, which is the category with objects being the predicates, so maps from X to V, and morphisms are maps from maps F from X to Y, such that P is less than Q composed with F. And now VSPred is quite similar, except now the objects are not single predicates, but subsets of predicates from X to V. Now we define the maps to be functions f x to y, such that when we pull back the predicates along f, so we mean that we compose Q and F, just like we did in the predicate situation, then we have that Q, so Q composed with X is also in S. And then the third category that is really relevant for us is VCAT, and that is a category of relations on X to V, and relations in particular that are reflexive and transitive. So reflexivity in particular means that the distance from an element into itself is greater than 1 for all X. And transitivity means that bulleted D is less than D. So in particular, these conditions they emulate this idea of if you have a hemimetrics, then there is this concept that it should have dxx is 0. So a distance from an element to itself should be 0. And then transitivity in a quantile way is the triangle inequality. So it reflects that. And that's, so VCAT actually gives us the category of hemimetric spaces. And then if we also add symmetry, which is that the distance dxy is the same as dyx, then we get the category of pseudometric spaces. This is very embarrassing, but I need to charge my laptop. So I will just do that in a second, and I will be back. Pardon.
Okay. Yeah, so probably I will just take over then. But then, so Johanna,
I'm actually back if you go.
Yeah, so Johanna, we're actually kind of short on time. Maybe you can just stop the screen share and I can start mine.
Okay.
Just go a bit over the remaining slides in whatever time we have left. Share screen. Relevant, I guess. The remaining slides in whatever time we have left. Share screen. Relevant, I guess.
So, okay, so this is actually going to be a bit tough to do in the remaining time, but let's see. Okay, anyway, so we have these v-valued predicates, and we also have this notion of v-valued categories. And as Johanna was saying, that these are essentially a generalization of metric spaces. And so one thing that exists between these two categories, so this one category of metric spaces and this category of sets of predicates of these, is an adjunction. And this adjunction comes in two parts. So if you have a set of predicates, then from these you can actually compute a distance, which just arises by evaluating all these predicates and taking the maximum distance that you get. But because we're in quantiles, the maximum distance actually turns into an infimum. And then conversely, if you have a distance, then you can extract from this distance the set of non-expansive maps, or V functors in quantilic parlance. And so one thing that we worked out during the week was that these two actually form a fibered adjunction, so not just an adjunction, but one that actually represents, works well with the underlying structure of sets. Okay, and then I guess I'll do the control ridge lifting and then still say what compositionality for that means and skip the rest. So the thing is, if we have a so-called predicate lifting, where's that slide? Oh, there's that slide. So a predicate lifting is something that turns a predicate on some set X into a predicate on some set Fx. And one simple example of that would be this second one here, where say we have some predicate that is valued in the unit interval. And we want to turn this into a predicate on the set of probability distributions. And one way of doing that is just, well, this thing P can be thought of as a random variable, so we can take its expected value. And taking this expected value actually turns out to be such a predicate lifting. And now, if you have a predicate lifting, or actually a set of these predicate liftings, then this gives you a map from sets of predicates to sets of predicates, where we just take all the predicates, take all the predicate liftings, and combine all of these. So this one should also include some set comprehension over elements, small lambda of large lambda. And the idea behind the control ridge lifting is that if we have this map on the category of sets of predicates, then using this adjunction, we can turn this into a map on the V categories. And this is highly abstract, but it turns out that if you instantiate this just right, actually using this expected value modality, then what you get is the original control ridge construction from, I think, the 1940s, which was motivated by transportation theory. But now we do this in this highly general way. And so the question that we concerned ourselves with during the week was that of compositionality, which is essentially, oftentimes we consider coalgebras of composed functors, so functors that are actually the composition of two individual functors. And if you want to lift these, then ideally what you want to do is lift the two functors individually and then compose these liftings with one another. And the question is really, so if you do this, does this sort of lifting agree with the composition of predicate liftings? And yeah, we did a lot of work on that. We got a few negative results. We got a few positive results that are actually a bit brute force-ish and where you need lots of these predicate liftings. So we did some work to improve these. Yeah, the up-to techniques I will not talk about very much. So here's a few of the results that we got. So we got some negative examples where compositionality fails. We got some conditions under which compositionality holds. As I mentioned, this is the first point. We established this fibered adjunction. Then we also proved some generic version of the so-called McShane-Whitney extension theorem, which is basically something about this VS spread. Right. We have a few pictures. Those were nice. So we worked in groups of 2 and 3, and we found that to be working quite well. And we also have still a bunch of homework to do if we actually want to eventually make a publication out of this, but we're decently confident. All right.
Paul and Johanna, this group was mentored by Barbara Koenig. Okay, I don't know, does anyone have a really quick question they want to ask? If not, Paul will be here for the conference.
Probably better to do this. I'm happy to tell you more about this.
Yeah, okay, thank you. Anyone from Chris's group? Do you have an online? Will be here for the conference.
Probably better to do this. I'm happy to tell you more about this.
Yeah, okay, thank you. Anyone from Chris's group? Do you have an online presenter?
Yes,
Okay,
it's me.
great.
I'm presenting online.
Okay, excellent.
Okay. I can't tell. There it is. Okay, great.
This is work. Yep. Okay. So we're going to present you our project for the Adjoint School, which is called Concurrency in Monoidal Categories. So we can go next slide. Sorry. Okay, thank you. So we know, and we saw with the first group, that a category represents processes, and a monoidal category represent. Sorry, it's weird to speak in a mic. Okay, that's bad. Okay. Oh, yeah. So in a monoidal category, we have objects that are resources, and the transformation are the morphism. And so morphism from A to B is something that transforms the resource A into the resource B. And so the nice thing with the monoidal setting is that the tensor product gives us a way to do parallel transformation. So F tensor G is the transformation F in parallel with the transformation G. Okay, so this is cool, but this is only in the time direction. Then the natural question that arises is, can we ask where those transformation happens? So if I want to know where is something, what I do usually is topology. And if I want to do topology and category theory, what I do usually is sheaf theory. So a sheaf on a topological space, it is simply a pre-sheaf that is valued in V, and V can be, I don't know, like a set or abelian groups or even the category of monoidal categories. And V will represent some data that we associate to our space. And so this pre-sheaf has to satisfy some kind of condition. And this condition tells us that for any open cover UI of U, the data of the pre-sheaf on each of the UI is equivalent to data on the pre-sheaf of U. So we can reconstruct the data on the whole open with all the data on the smaller opens that cover it. Okay, so now that we have our category of sheaves, so all the pre-sheaf that satisfy this condition, we ask, can we recover the structure of the topological space of the topology from this category? And so we can prove that we have a correspondence between the open set of our topology and the subterminal object. So the slogan is that the topological data of a Cartesian category can be found by studying its subterminal object. So we have a Cartesian category, and we can find topological data of a Cartesian category by the subterminal object. So just by doing a slight conceptual leap, slide, we can generalize that to a monoidal setting. So if I said the exact same sentence, I take a monoidal category, And then its topological data will be found by studying its subunit, so the morphism from any object to the unit of the monoidal category. And in fact, so theorem, if my monoidal category is nice enough, it doesn't really matter, we can recover like exactly it by studying sheaves on a topological space. And this topological space is constructed from the subunit. Like the subunit, they form a lattice, and lattice, we can transform it into some kind of topological space. And then by taking the sheaves on it, we can recover the monoidal category. And so this theorem, this result generalizes, for instance, the stone representation theorem that says that Boolean algebra are the same thing as the space. Okay, so this is the general idea, but then the subunits, there are too many of them, and the topological data, in fact, is stored not in all the subunits, but in the one that are called central idempotents. So what is a central idempotent? Well, that's something that is idempotent. So, okay, sorry. So a central idempotent is a subunit that is idempotent and central. So the idempotency means that if I take U tensored with U, then I get U back. And so topologically, if I take an open set and I intersect it with itself, I get the same open set. So in terms of, like in the monoidal setting, it means that this string diagram is an isomorphism. Subunit is the U tensored with U. And so this has to be an isomorphism. And also it is central. So it is central means that it commutes. It's not really important, but it means that, I don't know, U intersected with A is the same thing as A intersected with U. Objects that we want to study to take the data from a monoidal category. So next slide, yeah. So the result is that the set of all central idempotent is a mid semilattice. So really it means that tensoring acts like an intersection. And under some condition on the category C, we can prove that it is a frame. And so what is a frame? So a frame is exactly the structure that have the open subset of a topological space. So that means that really this lattice of a central idempotent is really like a lattice of open subset of a space. And so as a corollary, like a high-level corollary of this theorem, it means that given a transformation of resource in a monoidal category, it makes sense to ask where it happens. And so where does it happen? When we can take this morphism and we can, at all the subunit, it factor through. And so this set of subunits will give where this transformation happens. And so this is the starting point of our project. Given two disjoint subunits, so two transformations that are happening on two disjoint regions of space, how can we make them communicate? How can we add some bridges between like regions of space that have no intersection?
Thank you. Can everyone hear me? Yeah. Great. I'll assume I'm able to be heard online. I'll try to keep this short out of respect for time. Ari, who's going to talk after me. If you saw my talk at noon, this will not surprise you. So yeah, let's segue into a more concrete example. So here we have a diagram that represents the problem of extending a pre-sheaf. So looking at the bottom level of this diagram here, we have the structure of our space. We have a topological space. These arrows here are coming from the inclusion space in another. So we have some bottom element, we have a top element, and these two are both included in here. And we have a pre-sheaf. So on this top level here, we associate with each of these locations some behaviors, some actions that are being performed. And this is a sheaf when, well, what is the sheaf condition? When all of these actions mesh well with one another. So someone's not trying to send a message when another person is trying to receive it. No one's stepping on anyone else's toes. But what's unfortunate about this situation here is that there's no place for U and V to communicate. Actually sounds better when I talk towards the floor. So there's no place for U and V to communicate. They both are included only in the empty set here. So what our problem is to extend this pre-sheaf here to a pre-sheaf that contains a space where U and V can communicate with one another. And we call this space in this example W. And we want to find the sheaf that fits well over here, and it's also informed by the original sheaf we had on our starting structure. Next slide, please. Yeah, so this is a concrete example. This is the producer-consumer problem. We want to do things like avoid deadlocks, so we don't want to have someone producing when someone is trying to consume, and vice versa. And here, these dashed arrows represent like a sub-diagram of this inclusion diagram. So here we have a producer who's living in the space that was like U on the previous slide. We have this consumer who's living on a space like V on the previous slide. And they're communicating in this place called T, for like a space where each of these two people can talk to each other or transfer information. And so this is the general problem that we want to solve. I'll pass it off to you, Ari.
Okay. Let me turn my video on. Okay. Hi, everybody. Yeah, so I'll just talk a little bit about kind of our problem solving process and then some work we still have to do. So what we had been, what I think Luke was trying to explain was that what we did for like the first half of the research week was we would look at the semi-lattice of central idempotence and try to like throw in these new locations and then take the free distributive lattice on that lattice. And it turned out that was like something we could not deal with. It was too big. It was a big mess. And moreover, we realized that we couldn't specify, oh, just these two guys can communicate, or like these like two pairs can communicate. We had to make everything communicate or nothing. So we needed a new approach, and we were like, okay, let's instead try just freely adding morphisms between these communicating central idempotents. And I mean by that, let's start with a monoidal category C, and then take any old monoidal category G, whose objects are the central idempotents of the monoidal category we started with. And the only other thing about that G is it should admit a faithful functor from the central idempotence of C viewed as a category itself. And that functor should be the identity on objects. But this looks a little weird. So what I'm trying to say is we have a lot of freedom in specifying G now. So we could take G to be the free category on a graph of our choosing, as long as its vertices are ZIC. So you should think of G, this G as, this is just ZIC, but we've thrown in some new arrows. Cool. Okay, so the next thing we want to do is form this push out in the category of monoidal categories. And what we get from this is a functor that is injective on objects from C to this push out C hat. And we hope that C hat is going to be a new category where the guys we want to talk to each other can talk to each other. So here's our proposition. This push out has the same objects as C, and its morphisms are all formal string diagrams that are built from morphisms of C, so morphisms we originally had, and T phi, so this functor, this push out T on the right, and these T phi for morphisms phi that were in G. So this is what we mean by freely adding. Okay, and here's kind of the idea of the proof, which we haven't gone through in great detail yet, but we want to construct the amalgamation, which is something we have a nice recipe for, of this category G and our original category C. And then we just check that the morphisms are what we want. And so what's an amalgamation is just a special kind of push out in the category of monoidal categories. And like I already said, we know how to do this. We just have to sit down and actually do it. Okay, so here are some questions for the near future, hopefully. First of all, what are the central idempotents of this new category? So we know that we have an injection between the central idempotents of our old category and the central idempotents of the push out C hat. But we hope that C hat has some new central idempotents, so some new like locations for agents to communicate in. And then we'd like to know how to build the structure sheaf on C hat. So if you were in the Adjoint School and you read Chris's paper on sheaf representations of monoidal categories, we think the construction should go something like that. And then the paper that Luke just mentioned, Montero and Pereira, with their model of the producer-consumer problem, we want to check to make sure our model fits with theirs. Yeah, and I think that's all we have. Here are our references. Thanks, everybody. Thanks all the organizers.
Okay, thank you. Hello. Thank you, Ari, Clemence, and Luke. And this group was mentored by Chris Hunan. We actually have time for one question. Oh, here we go.
Thanks. This is pretty cool. I have more than one, so pick one. What are these conditions on a monodal category to get a frame of subunidal objects? You sort of suggested that they were light, but I feel myself wanting like colimits to commute with the tensor and then also some kind of image factorization, and maybe that's nice with the techno, blah, blah, blah. What do those look like?
Well, the condition are some kind of condition of on the lattice of subunit, like the lattice has to satisfy some set of properties. Exactly which one you can read it in the CRISP.
Oh, okay, so you just write it in terms of the lattice and more so than in terms of the tensor. Okay, thank you.
Great. Okay, anyone from Dan's section wanting to present? Great, thank you. Thank you.
Oh, this is fine, I think. Hello. Yes. Hi, everyone. Today we're talking about relating structure and power using game comonads, and with the subtitle of Towards Generalizations of Modal Logic. I'm Richie, Selena, Tyler, Jishwan, our teammate, is attending virtually, and we would just like to thank Dan and Nihil for being our mentors and TAs.
All right, let's get into it. So briefly, we're splitting this talk into sort of quick background material for people who have never seen this stuff before, and then we're going to talk about what we specifically did during the week. So we need to ask these questions. What is finite model theory and why do we care about it? These are two important questions to answer. So very loosely, finite model theory studies the expressive power of logics on finite structures. So these are things like finite graphs, databases, structures of interest to people like computer scientists, because computer scientists represent things in finite ways. So get some quick preliminary definitions out of the way so we can move on. So we talk about these relational vocabularies. Sigma is just a collection of relation symbols. Each of them has an associated arity. And then once we have fixed some vocabulary, we can talk about structures in that vocabulary. So a sigma structure is just a universe, which is a set, and an interpretation of every relation symbol in our vocabulary as an actual k-area relation on that set. So for example, you can think of graphs as sigma structures where you take sigma to be just a single binary edge relation. So how do we actually tell if two structures are the same in some logic that we're interested in studying? Well, the answer to that question is we play games on our structures. So specifically, we play these types of games called spoiler duplicator games. So you have two players. One player is the spoiler. Their goal is to show that two structures are different. And the other player is the duplicator. They're trying to say, no, these are the same structures. So, you know, the change my mind bro here is the duplicator. They're trying to say that this obvious deer is actually a horse. The spoiler, unfortunately, doesn't know the word horn. So this is sort of analogous to the spoiler not having the expressive tool in their logic to differentiate a horse from a deer. And so sort of formally, we can say, well, a structure A is equivalent to B in some logic L. We can define that as saying, well, if for every formula in our logic, A entailing that formula bidirectionally implies that B entails that formula. And so a specific example of one of these games that is really important for us is this game called the Ehrenfeucht Frasse game. I'm not going to pronounce that anymore. I'm just going to call it the EF game from now on. So the reason why this EF game is important is because there's this theorem that basically says if you can show that two structures are equivalent, or if there's a duplicator winning strategy in the K-round EF game that's equivalent to the structures agreeing on first order logic formula up to quantifier rank K, meaning like, you know, you have your 4 alls and your exists and K of those. Not actually K quantifiers, but quantifier rank. And so this third condition here might be striking a little interest, which is that this third equivalent condition is also that there is a co-Kleisli morphism from EK applied to A into B. So that's what we're going to be talking about now. So basically, this game Comonads project is about comonadifying these model comparison games. So EK is a comonad on the category of sigma structures. So basically what that means, well, we need to take a sigma structure, A, and we need to construct a new sigma structure, EKA. How do we do that? Well, we need a universe for this new sigma structure. This universe, basically we just take A to the set of spoiler plays. So these are like non-empty sequences of elements of A up to length K at most. And then the co-unit of this comonad just returns the last move of a play. And then we can also define how it acts on relations and also this co-Kleisli lifting operation, which are we're not going to talk about too much in the interest in time. But then, so the question is, how do these actually encode one of these model comparison games? So we can think of a function from EKA to B as sort of like a duplicator response to any given play that the spoiler can make, right? So like given some sequence of plays in A, the duplicator gives an element of B. So we can think of these as like duplicator strategies. And then the fact that F is a homomorphism of structures means that it has to preserve relations. And so in particular, the way that the comonad acts on relations implies that the duplicator strategy is actually winning. So this is why there existing this co-Kleisli morphism is equivalent to there being a duplicator winning strategy in this game. And then the co-extension is just sort of modeling the history preservation of the game. So, oh, right, yeah, forgot to mention. So we can like sort of read off from this definition what this actually means in terms of a game, right? So basically the way this game works is the spoiler picks an element of A, the duplicator responds with an element of B, and then the duplicator wins if after K rounds, the chosen elements form a partial isomorphism between the two structures. So we kind of figured, since this is a category theory crowd, we would present the comonad first and then tell you what the game was. So up to you whether that was successful or not. So yeah, turn it over to Richie now.
Thanks, Tyler. So yeah, we talked about these game comonads, and it's great. But why are we actually interested in them besides being at ACT, right? So the first reason we care about these game comonads is because it gives you like a way to capture these different model comparison games in a single abstraction. So it's a more uniform way to look at these things. Because if you look at the games descriptions themselves, they all look very different. but when you turn them into comonads, they're going to have the same sort of algebraic structure, right? So that's the first reason. The second reason is once we have these game comonads, we can start looking at the coalgebras of the comonads. And it turns out that these coalgebras of the comonad, specifically EK, they correspond to some combinatorial property. So if you take the K, the index of the comonad, that K corresponds to the tree depth of something that is called the tree cover of the Geifman graph induced by the sigma structure of A. And if you can do the same for other comonads. So here we have the pebbling comonad and the modal comonad, which we don't have time to get into, but they correspond to the tree width and the synchronization tree depth respectively. Yeah. Oh, no, yeah, that's fine. Go back. So yeah, as a quick recap, that was kind of the background of finite model theory and game comonads. And then now we're going to talk more about what we actually did in this research week, which is applications to modal logic generalizations. So what are we doing? So first order logic, most of you know what first order logic is. It's very useful for encoding your problems. Most of your problems in life can be turned to a first order logic thing. So that's good. But now if you want to study your thing as a first order logic formula, and you ask questions like, is this formula always satisfiable, or is it sometimes satisfiable, or is it never satisfiable? These sort of things, the SAT problem of this logic is undecidable. So there's no algorithm that can decide it in finite time all the time. On the other hand, there's this other logic called modal logic, which is not as expressive as first order logic, but is robustly decidable. So it can be efficiently checked whether it is a statement is sometimes true or always true, and so forth. And it turns out you can view modal logic as a fragment of first order logic. So we have this thing that is powerful, but we can't prove things about it, and we have this thing that is less powerful and we can prove things about it. So the question is, can we extend this weaker thing, modal logic, to something closer to first order logic without losing the SAT property? And the answer turns out to be yes. And we're going to study these two fragments called the unary negation fragment of first order logic and order fragment of first order logic. So we're going to find games and game comonads for them. So the first fragment, the unary negation of first order logic, looks pretty much like the first order logic. And you can see kind of its signature. This is how you define it. You have variables, you have relations on these variables. You can do disjunction and conjunction of the formulas. You can do existential quantifiers, equality. And the only catch is when you do negation, you can only do negation on formulas with at most one free variable. And a consequence of that is because you can build the for all using existential quantifier and negation, you can only do for all on formulas with at most a single free variable, and which is limiting. Another thing you can't do is you can't apply negation to x equals y because there's two free variables, right? So that's another restriction that is not very great. We'll talk more about that later. So here's a property you can express. You can express that these vertices form a cycle, full cycle, I think. And then
That was the last R is supposed to be an E.
yeah. But a free cycle actually, and then this other property you can't express because there's free variables and there's two of them and you're negating it, so you can't express that.
Okay, so we've talked about games. So what's the game for the uniform logic? So this is the one that is given in the paper where these logics are introduced. The idea is we have two structures as usual. We have a starting position, which is an element of A cross B. And then Spoilers chooses a structure. Let's just say A for because it's easier. And then chooses a finite subset V of A. And then the duplicator needs to find a partial homomorphism defined on V such that the image of A is B. So we have a pair that we have to keep. And then once the duplicator has done that, the spoiler chooses another element of V and fixes a new pair. And then we restart. So the duplicator wins on a K round if such a partial homomorphism can be done. So if they can go through step 3 of this. And now the thing is this game is really nice, but it doesn't have the same structure as the other games that we have, which means that it would be a little harder to find a comonad for it. So the first thing we did was find an equivalent game that was closer to things that we have in the literature. So we will have the Pebble UNFO game. And the idea is we have two structures. Spoilers chooses one of them. And as long as we stay on the same structure, the game goes exactly like in the EF case. So spoiler chooses an element of A, duplicator chooses an element of B, and we go on and on and on. And the problem is, the moment spoiler chooses to change structure, so to go to B in this case, they will choose one play and forget everything else we've done until now. So we kind of clean the board. And then the game continues as in the EF case. And the duplicator wins a round if the current board, so not talking about things we've forgotten, forms a partial homomorphism. Now, there's a variant, slight variant of this, where instead of letting spoiler choose a play, we just keep the last play and forget everything that happened before that. And we have mostly proven that these two versions are equivalent to the original UNFO game. And we'll have an example of this, and because it was Richie who found this example, I'm going to let him do it.
Yeah, thanks, Elena. So we're going to use the games that we shown earlier to be equivalent to the original UNFO game to actually prove something, right? So we're gonna walk through the utility of these model comparison games. So we're specifically gonna prove that this property that I've expressed here in first order logic can't be expressed in the unary negation fragment. So how does this work? We have two structures, A and B, and these edges represent binary relations, so B and R respectively, blue edge, red edge, and you see that the structure A satisfies this property where there is a pair such that there is a blue edge but no red edge and no orange edge. But B doesn't have that, because for every pair of vertices, if you pick the vertex twice, there is both a blue edge and an orange edge. So A satisfies it and B does not. But you can't win this game, the UNFO game. So it turns out there's no UNFO formula that can distinguish these two things. So therefore, this property can't be expressed. So as Tyler said earlier, like this, they know what a horn is. Like, this is our horn. Like, you see. Okay, so this is how the game works. The spoiler is going to play on the side A because it's the more interesting side. Let's say they, without loss of generality, choose A1, that vertex, and then duplicator is forced to choose B1. And you see at all times, there is a graph homomorphism from A to B, right? You can see that this subgraph is the same as that subgraph, obviously. And after that, the next step would be the spoiler would choose the other vertex, because that's the more interesting thing to do. Like, you can check the other cases as well. And the duplicator is forced to choose the same vertex on their side again. And you see there is still a graph homomorphism between A and B, the subgraph induced by these vertices A and B. Specifically, if you see A1 and A2, that edge is still preserved in that relation. The fact that there is an orange edge, it doesn't matter, because we just need to preserve relations and not reflect them. And the extra thing about the game is the spoiler can switch sides on the board, and they can now play from B, but they have to discard all but one set pair of vertices, right? So now they're playing from B, and they have B2, and B2 corresponds to A2. And you can see, obviously, there's still a graph homomorphism between these. So, and now if they play B1, or if they play B1 now, they're going to play A1 on the same vertex, and this game becomes really boring. So you can see there's no way to tell these two structures apart in UNFO. Therefore, this property can't be expressed, because that would tell them apart. Yeah.
Thank you. So we are an applied category theory conference, so we need category theory at some point. So coming back to the comonads, if you've been following, you've been reading the slides, you probably have noticed that the EF game that we've mentioned gives us formal, like a first order logic, existence of order logic. And that's because the game we were playing, we were forcing the spoiler to play on one side the entire time. So the way to find a construction that gives us the equivalence on first order logic period is to use this. So I'm going to wave my hands a lot on this part because we do not have time to explain all of this. But the idea is on the category of co-algebras in EK, we have this thing called open pathwise embeddings. And if we have a span of open pathwise embeddings, a duplicator winning strategy is the same as having one of these. The idea is basically that we can go from A to B and from B to A without losing any kind of information, because the open pathwise embeddings let us keep all the relations when you go back and forth. And the thing is, the UNFO game, we do lose some information. So how do we encode that? The idea we have is have two spans. So the idea is whenever spoiler is playing on A, we are on the first span. So we can go from A to B without losing information, but not from B to A. And then the moment a spoiler goes to B, we go to the other span, in which we can go from B to A without losing information, but not the other way around. Now the thing is, we need some kind of condition to link these two spans, and that is work in progress for now. And now the other logics we've been working with are the order fragments. So these are pretty much first order logic. The only things that we do is in relations, we force the variables to only appear in the order they've been introduced. So we have these three different variants. In the prefix fragments, we have to start on the first variable and then go over. In the fluted fragments, we have to go all the way to the last variable. And the infix fragment, just as long as they are in order, we're good. So you have some examples in case you need some kind of idea.
Yeah, so I know we're almost out of time. So basically, I'll just quickly mention the comonadification of these ordered fragments. So we basically did manage to find comonads for all three of these fragments. They essentially boiled down to being small modifications of the original EF comonad, where you just tweak what it's doing on relations. And then looking at the coalgebras was interesting because essentially what we found is that the existence of a coalgebra for each of these comonads corresponded to the structures that they're looking at being different types of forests of certain heights. So like one of them was a directed forest, one of them was an undirected forest but allowed one cycles, things like that. So yeah. Ongoing work, there's obviously a lot still left to do. So we need to, the first thing we need to do is extend these ordered comonads to allow variable rebinding, because we didn't capture that part of the logics. And the other thing is, yeah, we waved our hands about these coherence conditions. We have some ideas of how to do this, but we need to actually formalize them a little bit better. So yeah, that's game comonad.
Okay, thank you, Elena, Richie, and Tyler. That group was mentored by Dan Marsden. Does anyone have a question for them? Okay. If not, then let's give everybody in the Adjoint School a round of applause. Thank you so much for attending this session. Okay, we can break for